let's get started. So we have been talking about the importance of logic in the field of artificial intelligence, and we have said that logic is one of the most important ways in which you communicate with an AI agent. You express what you know about the world in a logical representation. You therefore enable the machine to make logical inferences, and you can then query the machine for new inferences or properties of the domain which it might be able to use the current knowledge to respond to. In that context, we talked about what is a logical representation, what is the syntax, what is the semantics, and we then started talking about inference algorithms, and we did one inference algorithm which is forward chaining. And forward chaining is this procedure where it typically uses horn clauses in the system, and it uses modus ponens rule to make inferences. So whenever the rule says that P1 and P2 and P3 up to Pn implies Q, and we know that P1 is true, we know that P2 is true, we know that Pn is true, then we can prove that Q is true. Okay. And we said that is it a sound algorithm? Yes. Is it a complete algorithm? No. But if the only kinds of rules in our knowledge base are horn clauses and the query is a single literal or a conjunction of literals, then it is complete. This is very well. And then we very briefly mentioned that there is also something called backward chaining, in which you sort of start from what you want to prove and then try to create more support for it by saying, okay, if I have to prove this, what should be true in my domain, and then if I have to prove this, what should be true in my domain, and I keep doing this, and eventually I get to what was originally true in the knowledge base, that would be search in the backward direction. So today our goal is to talk about resolution proof systems. This is equivalent to proof by contradiction. Okay. And for that, we will first talk about converting everything into CNF. Now, I want to mention that the reason we convert everything into CNF is because it's a canonical representation. Any logical formula can be converted into a CNF formula, and so we work on CNF formulas because we assume that if you have a different kind of formula, you will first do a basic conversion, give me a CNF formula, and then I will start working on it. Okay, so you always have to start with some representation for an inference procedure, and so they decided that they will use the representation of CNFs. They could have used DNFs, they could have used other representations, but they said they will use CNF. So far so good. So very briefly, how do we convert any formula? Let's say my formula is B11 bidirectionally equivalent to P12 or P21. So now what we do is we basically start applying rules in this order. First, if it's a bidirectional implication, we convert it into unidirectional implications. So A, if and only if B, can be equivalently said as if A then B and if B then A. Right? So B11 bidirectionally equivalent to this is equal to saying B11 implies this and this implies B11. So that's the first step that we use. We eliminate bidirectional implication and convert it into two unidirectional implications and a conjunction of those. So now you get B11 implies P12 or P21 and P12 or P21 implies B11. Now the next step is to convert implication into a disjunction. Every alpha implies beta is equivalent to not alpha or beta. So we apply that rule, and so we get not B1 or another disjunction, so that becomes like a longer disjunction. And then we have this conjunction here, and it becomes not of this antecedent or B11. Now at every step we ask the question, is it in CNF form? And CNF form is a conjunction of disjunctions. So is it in CNF form right now? Is the first part a clause? Remember, what was a clause? A clause is a disjunction. So is the first part a clause? Yes. Is the second part a clause? Only disjunctions are allowed, but there is a not in a parenthesis. So therefore it is not a clause. So whenever I have not A or B, I can bring the not inside using which rule? De Morgan's rule, right? So not alpha or beta becomes not alpha and not beta. So that is what happens. You get not P12 and not P21. You don't have to touch the first part because it's already a clause. Now is it a clause on the right? It's still not a clause because we have a conjunction in the parentheses and then a disjunction outside. We only need conjunctions outside and all disjunctions inside, right? So when this happens, you apply distributive law. And so in this distributive law, what would happen is that you will make one conjunction which is not P12 or B11, and you will make one conjunction which is not P21 or B11. And now you have got a conjunction of disjunctions. You got it in the CNF form. It's a conjunction of clauses, so you are done. Any questions on this? So always start removing the syntactic sugars, the bidirectional and the unidirectionals. Once you do that, everything has only not, and or. Then you apply the De Morgan's and the distributive law appropriately to finally get to a conjunction of disjunctions, a CNF formula. So now for the rest of this lecture slides, we are going to assume that anything that is given to us is in the CNF form. We will not worry about anything else because we know that anything can be converted to CNF. So now let's talk about resolution. Now the basic tenet of resolution is this rule. If I have a clause P or alpha and another clause not P or beta, or in this case not P or beta or gamma, then we can prove that alpha or beta or gamma. And let's think about this. We know that either P will be true or P will be false. We may not know its value. But if P is true, what has to be true? Beta or gamma has to be true because we have a clause which says not P or beta or gamma. Now not P is false. So therefore beta or gamma have to be true. Similarly, if P is false, alpha has to be true. It's like saying if this happens, then you have to do A. If this does not happen, you have to do B. So therefore, you know that you either have to do A or you have to do B. This is what this rule is saying. So this is the basic resolution rule. And now we have to ask the question, is it sound as a rule? Like modus ponens was sound as a rule. Is this sound as a rule? Yes, right? So whenever resolution says S1 proves S2, then you know that S1 entails S2 in the world. What is even more beautiful, right, is that it has one kind of completeness. It is not complete. In fact, there are theorems which say that Gödel's incompleteness theorem. You know about that, right? Which basically says that you cannot have a proof system which is sufficiently expressive and also complete. So you cannot build something which will prove everything if the problem is any interesting, right? So actually when Gödel proved this, everybody was like, wow, we can't do anything, this is so sad. Because you can never create a complete proof system. But you know, over time AI researchers realized that all this incompleteness business is good for theory. We will just make systems that work and then we will make different kinds of proof systems. So if you have that kind of problem, use this, and if you have another kind of problem, use that. It needs to work in real world. It doesn't have to solve every problem in the universe. So anyway. So this is called refutation completeness. Refutation completeness means that I may not be able to prove everything, but if it is unsatisfiable, that means that if it is not satisfiable at all, if there is no model for the formula, if there is no world which is consistent with this set of assertions, then it will be able to prove false. And how would it be able to prove false? By creating an empty clause. Remember, we talked about the fact that empty clauses are equivalent to false, and you will see it very soon in the as an example. So, very first point that I want to make is that resolution already knows about modus ponens. Anything that modus ponens can do, resolution can also do. And to show that, I have to show you that if A implies B, then A entails B, right? So, if I know that A implies B and I know A, then I will entail B, right? So, let us write this out. So, we will first create clauses. So, if A implies B becomes not A or B, A is A, and then let us apply resolution here. Let us apply resolution here. What would resolution say? What is P here in the so there was a P in the previous slide. What is the equivalent of P here? A. We are looking for that thing which when is true you do something and when is false you do something, right? So, A is that thing. There is A somewhere in the clause and there is not A somewhere in the clause. And when you resolve them, then you add everything else that was the disjunction and create a new clause for it, right? So, in this case, we said pure alpha, not pure beta or gamma. So, resolution leads to alpha or beta or gamma. So, similarly, in this case, not A or B, A that leads to B. We get rid of A and not A and we are left with B, which is exactly what modus ponens says. So, the first thing is that resolution is stronger than modus ponens, it knows more. So, you can think of it as symbol pushing, you are just pushing symbols down, right, by creating new formula, and the rule is very simple, right. Now, I also want to show you with a very simple example that it cannot prove everything. And here is an example. It's a terrible example, but it makes the point. If Will goes, Jane goes. If Will doesn't go, Jane goes. Will Jane go? Answer? Yes. Should resolution be able to prove this? You think so. And I will tell you why it is not able to. If you resolve these two, you get J or J. Do you get J or J? Now, does it know J or J is J? It does not know J or J is J. It's so stupid that it absolutely has no idea that J or J is J. So, just by applying resolution, you cannot prove this simple thing. But that's okay, don't worry about it, because it is refutation complete. What does that mean? That if something is unsatisfiable, you will definitely be able to prove false. So, how do we prove these facts now? What we do is we use proof by contradiction. So, we said this is what we know. What we know is not W or J and W or J. And what do we want to prove? J. Let us suppose J is false. This is what we do in proof by contradiction. Let us suppose what we want to prove is false. So, we assume not J and then try to come to a contradiction, in this case, or a false, in this case an empty clause. And here is a simple way in which you do it. You resolve not J and not W or J, you get not W. I mean, there are many ways to do this, right? And you resolve not W and W or J, you get J. And then you resolve not J and you get empty clause. If this example is not clear, don't worry. I will show you another example and we will do it slowly. But here notice that J and not J resolved to an empty clause. If empty clause was true, which is what we assumed last time, this will go completely mad. When J is true and not J is true, that means this formula is not satisfiable, cannot be true. So, when they get resolved and you get nothing, that nothing should mean false. And again you go back to how we discussed what is the zero of the disjunction operation. Okay. So, we are going to work on this particular example. If the unicorn is mythical, then it is immoral. If the unicorn is not mythical, it's a mammal. If the unicorn is either immortal or a mammal, then it is horned. prove that unicorn is hot. And I'm sure, I mean, you can go back to your Boolean logic and prove it one or the other, but we'll prove it using resolution. Okay. So, we will define symbols. So, let's say our symbols are M for mythical, I for immortal, A for mammal, and H for horned. And then we define formula or clauses. So, for the first statement, what is a clause? M implies I, and we will write it as a clause, not M or I. For the second, it would be M or A, right, and so on. So, these are my clauses for the input. Now, we will always prove it by contradiction. So, what do we assume? Not H, we assume not H, okay. And now our goal is to apply resolution repeatedly to get to empty clause. And there are many paths, so we will just look at one possible path. So, give me one resolution that you can do. For example, let us start with not A or H and not H. We get not A. Similarly, not H and not I or H, we get not I. So, we get these two by resolving. Then let us keep doing this. We resolve M or A and not A, we get M. We have not I and not M or I, we get not M. We have M and not M, we get empty clause. So, at least in this simple example, we were able to prove empty clause, and therefore, this is falsified, it is a contradiction, and therefore, unicorn is horned. Now, we know. Everybody with me? Any questions on resolution? Now, I am not going into the detail of how do you actually implement resolution very much. Of course, you do search, right? There is just no way around it. So, you have a database of clauses, and you negate the goal and convert it into clausal form, and you add that to the database. So, now you have a full database of clauses and the negated goal. And then you loop, you basically select which two clauses you need to use resolution on, and generate a new thing, and you put it in the database, and you keep doing this, right? And in order to figure out, which pair of clauses you put in, there you use search control strategies, right? Heuristics, some branching heuristic, and so on. And at some point, when you add empty clause, you have got success, you have proved it. And then, if you are out of loop, but you don't get an empty clause, you can't get something new, but you don't even get empty clause, you return failure saying that I can't prove this. And we have to make sure that we never resolve the pair of clauses more than once, and if multiple copies of something happen like Q or P, we just convert it into Q or P. So, we add that knowledge also in the system. Okay. So, this is called resolution.